Hello, this will be a demonstration of proposition 18 from book 6 of Euclid's Elements, which requires us to, on a given straight line, describe a rectilineal figure both similar and similarly situated to a given rectilineal figure. What we're given is some straight line AB and some rectilineal figure CDEF. We're going to make C, D, shoot it up like that. Okay, so we're going to have some straight line AB and some rectilineal figure CDEF. And the task at hand for us is to describe on the given straight line AB a rectilineal figure similar and similarly situated to this rectilineal figure CDEF. We're going to begin by joining the straight line DF by postulate 1. Next, at the point A, we're going to make the angle GAB equal to DCF. That. And at the point B, we are going to make the angle ABG equal to CDF. So we're going to do that by proposition 123, of course, on a given straight line and at a given point on it to describe a rectilineal angle equal to a given rectilineal angle. So we're going to have the angle GAB equal to the angle FCD and the angle GBA equal to the angle CDF. Which means then, between the two triangles CDF and ABG, we have two angles which are equal to two angles, which means by proposition 132 and some other propositions, that the third angle, AGB, shall be equal to the third angle CFD. Watch the end of my 6.4 video to get a more full explanation of why if two triangles have two angles equal to two angles, the third angle will be equal to the third angle. But we've seen this enough times throughout book 6 that I'm going to simply state it without explanation. Which means then, the three angles of the triangle CDF are equal to the three angles of triangle ABG, which means by proposition 6.4 that in equiangular triangles, the sides about equal angles are proportional. We can say that FD is to FC, just as GB is to GA, that FC is to CD, just as GA is to AB, and that FD is to CD, just as GB is to AB, which means that alternately, we can say that FD is to GB, just as FC is to GA, and just as CD is to AB. We're going to alternate those proportions, of course, by proposition 5.16. So, we have that FD is to GB, just as FC is to GA, just as CD is to AB. Now, again, we're going to make the angle BGH equal to the angle DFE. Like that. And we're going to make the angle GBH equal to the angle FDE. That. Right. And we're going to do that by proposition 123. Which means, again, we have in the two triangles DFE and BGH, two angles which are equal to two angles, which means by proposition 132 and some others, the third angle GBH is equal to the third angle FED. Those are a lot of marks, but we have a lot of equal angles here. And so by similar reasoning, we can arrive at the fact that, the two triangles, because they're equiangular, they are similar to each other. That's proposition 6.4, which means, again, that FD is to FE, just as GB is to GH, that FD is to ED, just as GH is to HB, and that FD is to ED, just as GB is to HB, which is again alternately by proposition 516 that FD is to GB, just as FE is to GH, and just as ED is to HB. But we have four ratios which are equal to the same ratio FD to GB, which means they are all the same with one another by proposition 511, so that FC is to AG, just as CD is to AB, just as FE is to GH, and just as ED is to HB. So all the sides of the two rectilineal figures CDEF and ABHG are proportional. Next, we're going to prove that the two rectilineal figures, we're just going to start calling them DF and BG, just calling them by their diagonals like we do with parallelograms, that they are also equiangular. So, the angle CFD having been made, or the angle AGB having been made equal to the angle CFD, CFD equal to AGB, we had shown that in the second step, and the angle DFE being equal to the angle BGH because we made the angle BGH equal to the angle DFE. We did that in step 5. If we add these two angles together by common notion 1, adding equals to equals, the sum shall be equal. And so the whole angle CFE is equal to the whole angle AGH. And we can prove by similar reasoning that the angle CDE is equal to the angle ABH by saying that the angle ABG has been made equal to the angle CDF and that the angle GBH has been made equal to the angle FDE, which means that common notion 2, if we add these angles together, the whole angle CDE shall be equal to the whole angle ABH, which means that we've shown that the two rectilineal figures FD and GB are equiangular. We made the angle GBA equal to the angle FCD. We have just shown that the angle CFE is equal to the angle AGH, and we've also just shown that the angle CDE is equal to the angle ABH, and we had shown in a previous part of the proposition that the angle GHB is equal to the angle FET, which means that the two rectilineal figures, FD and GB, not only are equiangular, but also have the sides about the equal angles proportional, which means they are similar according to definition 6.1. That's the definition of similar rectilineal figures. And so we've done that which we set out to do. On our given straight line AB, we have described the rectilineal figure GB, which is both similar and similarly situated to the given rectilineal figure CDEF QEF. There is a porism appended. No, there's not a porism. I'm thinking of the next proposition. There's no porism appended to this. It's a QEF. My bad. So, I actually have nothing more to say about this proposition. Actually, I do. So, the reason Euclid works with quadrilaterals here, as opposed to like pentagons or hexagons, is because, again, they're the simplest non-trivial case. If you had a 5-sided figure or a rectilineal figure with any number of sides, the process would be quite similar. You divide it up into triangles and you make the similar triangles, and then you show that the whole is similar to the whole. So you can follow this procedure, though it's only been given for quadrilaterals. You can follow it for any number of sides. And that actually being all I have to say about this proposition, I will end the video here and move on to 6.19.